SwayamPrabha. Digital India. Educated India.
So we stopped with the derivation of the transfer function of second order systems. We are considering the general governing equation of a second order system to be given by d squared y dt squared plus 2 zeta omega and dy dt plus omega n squared y, right, equals omega n squared u. And applying the Laplace transform and using zero initial conditions, we obtain the transfer function to be omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared, right? So that's where we stop. And we observe that the poles are going to be at minus zeta omega n plus or minus omega n times square root of zeta squared minus 1, right? So if we plot these poles, what's going to happen is the following. So I have the real and the imaginary axis in the s plane. So it so turns out that, like if we have the value of zeta to be between 0 and 1, we would have the poles to be complex conjugate, right? Because the poles will be still at minus zeta omega n plus or minus omega n times square root of 1 minus zeta squared, but then zeta squared minus 1, okay, but zeta squared minus 1 is going to be negative now. So what we do is that we just rewrite this as plus or minus j omega n times square root of 1 minus zeta squared, right? So just to make the the fact that the roots are going to be complex conjugate more clear, right? So we just flip the order in the square root and then add a j term, right? Because we are going to get a minus sign in the square root, okay? So we can immediately see that this is a pair of complex conjugate poles, right? And typically this omega n times square root of 1 minus zeta squared is denoted as omega d, which is what is called as a damped natural frequency. Okay, so that is the term given for that. Okay, we will see why it's called damped natural frequency shortly, but that's what it's called as. Okay, so omega n times square root of 1 minus zeta squared is omega d. So if you plot it on the complex plane, so we are going to have a pair of complex conjugate poles. The real part is going to be minus zeta omega n, and the imaginary part is going to be plus or minus j omega d, right? So that's what we are going to have as far as this particular case is concerned. And this case where we have zeta to be less than 1, okay, is what is called as an underdamped second order system, okay? So a second order system is said to be underdamped if the damping ratio, okay, is less than 1, okay? So that's the implication here, okay? Now that's for the first case, right? So the second case is when zeta is exactly equal to 1. We immediately see that the poles are going to be at minus omega n and minus omega n. So so we have a pair of repeating poles at minus omega n. Why is that? Because immediately we see that the Planck transfer function becomes omega n squared divided by s squared plus 2 omega n s plus omega n squared, right? When zeta is exactly equal to 1. So this can be rewritten as omega n squared divided by s plus omega n whole square, right? So the denominator becomes a perfect square, right? So that's why we have a pair of repeating poles at minus omega n. So I can say that, like we are going to have two poles at minus omega n, right? So that's going to be the second case, okay? And this case where we have zeta to be exactly equal to 1, and the poles to be repeating is what is called as a critically damped second order system. Okay, so that's the second case. Now the third case is when zeta is greater than 1. When zeta is greater than 1, obviously the poles are going to be at minus zeta omega n plus or minus omega n times square root of zeta squared minus 1, the same as what we calculated here, right? Because when zeta is greater than 1, zeta squared minus 1 is anyway positive, right? So we are going to have two real poles, right? So that's what we are going to have. So if we want to plot these two poles qualitatively, like what happens is the following. So one pole is going to be here and another pole is going to be closer to the imaginary axis. This pole is going to be minus zeta omega n minus omega n times square root of zeta squared minus 1. This pole is going to be equal to minus zeta omega n plus omega n times square root of zeta squared minus 1. Right, so that's this pole. Okay, so but the question arises, how do I know whether this pole is still in the left half plane? That is because please note that minus zeta omega n would be dominating the sum, right? So we can see that the magnitude of omega n times square root of zeta squared minus 1 will be lower than minus zeta omega n, right, for any zeta greater than 1. Okay, so we can easily observe that. So as a result, the value will be negative, but it will be less negative than the other pole. Okay, so that's the implication. Okay, so as a result, this one is the dominant pole. Okay, please remember our definition of dominant poles. Right, so the pole which is closer to the origin is what is called as a dominant pole. Right, so that is what is called as a dominant pole. Right. So such a scenario where zeta is greater than 1 and we have two distinct poles on the negative real axis corresponds to what is called as an overdamped case. Okay, so that's the overdamped case. Okay, now what is the physical significance associated with each of these cases, right? So because we have defined it based on the damping ratio, now what is the implication? Okay, so that's something which we are going to see. So as an aside, to just give us a feel of what we are dealing with, let's consider the mass spring damper system that we already looked at. Do you recall what was the transfer function for the mass spring damper system? It was the ratio of the Laplace of the displacement divided by the Laplace of the force input, right? Correct? So what did we get it as? It was 1 divided by ms squared plus cs plus k, right? Am I correct? So if you want to bring it to the same form as what we the Planck transfer function that we have derived, let's divide both the numerator and denominator by m. So this will give us 1 by m divided by s squared plus c by ms plus k by m. Correct? So if you compare, this implies that omega n squared is going to be equal to k by m. That means that omega n is equal to square root of k by m, right? This is a well-known formula for this 1 degree of freedom mass spring damper system, right? What is the natural frequency for that system? And 2 zeta omega n is going to be equal to c by m. So this implies that zeta, the damping ratio, is going to be c divided by 2m omega n. This implies that zeta is going to be equal to c divided by 2 square root of mk. Right? So you see that even if I have a mass spring damper system, I can correlate the damping ratio and the natural frequency to the parameters m, c and k. Okay. So zeta being greater than 1 or less than 1 or equal to 1 depends on this ratio, okay, that we have obtained here, c divided by c divided by 2 square root of mk. Okay, so that's what decides what is the value of zeta. Okay. So now the question arises, like what do we mean by natural frequency of the system, right? So damping ratio, as we can observe, like is indicator of the amount of damping that we put in, right? Because C indicates the damping coefficient, right? So what is the amount of damping or energy dissipation that we have in the particular system, right? So what do we mean by natural frequency?
C was 0
Uh-huh.
and the frequency at which the
System
will oscillate.
oscillate, is it? Is it the complete answer, or you want to add something to it?
Even when there is no external force,
Okay.
there should be no external force and no damage.
Okay.
If you consider the free response of the system,
Okay.
under that, if you impose the restriction that there is no damage.
Okay. So I think that completes your answer, right? So that's good. So what is natural frequency? Like if you do not have any damping to begin with and no external excitation, the frequency with which the system's response would oscillate if there were an initial perturbation, okay, what we call as the free response of the system. Okay. So as homework, I want you to do this. Please do this. Okay. As homework, consider u of t to be 0 in the above governing equation. Okay. Y of 0 is not equal to 0, y dot of 0 is also not equal to 0, but zeta is 0, right? That's the undamped case. Okay. So what is the system that we are dealing with? Y double dot t plus omega n square yt equals 0. Okay. So get the apply the Laplace transform and get, what to say, apply the Laplace transform. Okay. Of course, now we need to be a bit careful, right, because the initial conditions are not 0. Okay. And calculate the free response. Okay. Then you will immediately get the answer, right? So you will see that the output term will have sinusoidal terms whose frequency is omega n. Okay. So that's the definition of natural frequency. Okay. So this is something which I want you to do, okay, and find out. Okay. That's the definition of natural frequency. Is it clear? Okay. So this is the case of the overdamp system. Okay. Like, so that's when zeta is greater than 1. So please do these things, right? Now what we are going to do is that, like, let's consider the case of the underdamped system and calculate its unit step response. Okay. So underdamped system means, like P of s is going to be once again omega n square divided by s square plus 2 zeta omega n s plus omega n square. Okay. So please remember the poles are at minus zeta omega n plus or minus j times omega d. So before we go further, like some more notation with respect to underdamped second order systems, because these become useful later on. So if I plot the real axis and the imaginary axis, and then we have the S plane, and let's say these are my two poles, complex conjugate poles. The real part is minus zeta omega n, right? The imaginary parts are j omega d and minus j omega d. So let us say I draw a line from the origin to this pole. Okay, what is the length of this line segment?
Negative omega d square plus
Yeah.
d square omega square.
Yes, what will that be? Omega n, right? So the length of this line segment, like which is drawn from the origin to the pole, to any one of these two poles will be omega n, right? Because this horizontal, the adjacent side is going to be magnitude is zeta omega n. The height is going to be omega d. So if you use the Pythagoras theorem, square root of zeta squared omega n squared plus omega d squared. Omega d squared is going to be omega n squared times 1 minus zeta squared. So you will see that things will cancel, you will get omega n, right? Omega n will be the hypotenuse, okay, of this right angle triangle. Now let us say we call this as beta. So we note that cos beta is equal to, what is cos beta? Zeta, right? That's it, correct? Because the adjacent side is zeta omega n, hypotenuse was omega n. So zeta omega n by omega n, it will be zeta, right? So cos beta is equal to zeta, right? So that's something which we should remember. So in other words, what I'm saying is that the cosine of this angle which is made is equal to the damping ratio of the system. Okay, please remember this. So if you increase the damping ratio, what do you think will happen to this angle beta? It will decrease, right? And vice versa. Okay, so please remember that. So let us calculate the unit step response of this underdamped system. Okay, so let us calculate its unit step response. So unit step response means u of s is going to be equal to 1 by s, right? So y of s is going to be p of s times u of s, okay, which is going to be omega n square divided by s times s square plus 2 zeta omega s plus omega n square. So what will happen here? How do I do partial fraction expansion? We discussed this, right? Maybe a couple of weeks ago. So you can do it as a by s plus bs plus c, right, divided by s square plus 2 zeta omega n s plus omega n square, right? So you can of course like factorize the denominator polynomial into two first order polynomials with complex conjugate roots. I think we did one example, right, where we did it in two ways. We factorized as two first order polynomials with complex conjugate roots, and what else did we do? What was the other method that we tried out? Sorry? Inverting the sign. So there is, if you had a second order polynomial which you cannot factorize as two factors with real roots, what did we do? So we did sum of squares, right? Yeah, so we can follow that approach also, right? So that's what we are going to follow here. Okay, so you can use both approaches, and I think we showed in one example that both approaches will give us the same answer. It doesn't matter. Okay, so if I do a by s, why do I do bs plus c divided by s square plus 2 zeta omega n s plus omega n square? Please remember, if I have a nth order polynomial as a in the what to say denominator of any partial fraction, the numerator in general is of order n minus 1. Okay, one order less. So one order less in this case is a first order polynomial. That's why I am having bs plus c. Now what will be the values of a, b and c? Can you calculate and tell me? Calculating a is pretty easy, right? Multiply both sides by s and substitute s equals 0. So a is going to be 1. If you multiply both sides by s and s, substitute s equals 0, you get 1. So what about b and c? Are there other ways to figure out b and c? You know, I will give you the answer. Okay, you please see, by now we should be familiar with partial fraction expansion, right? So I will give you the answer. You please do it as homework. Okay. So this is the partial fraction expansion, right? So you can double check it by taking the LCM. So you will see that you will be left with omega n squared in the numerator, right? Okay. So that's what we have, and so this will be 1 by s minus. What we are going to do is that in the numerator we have this s plus 2 zeta omega n. We are going to split it as s plus zeta omega n and then another zeta omega n. I can do that. Can I not? I'm just writing 2 zeta omega n as 2 terms. Now, in the denominator, how can I write this s plus 2 zeta omega n s plus omega n squared as a perfect square? What method did we learn? So, this will be s plus, what did I tell you? You need to basically first divide the coefficient of s divided by 2. So, coefficient of s is 2 zeta omega n. So, what do? You divide by 2. So, you will get s plus zeta omega n whole square, right? Then you subtract the constant, which is going to be zeta squared omega n squared. Okay, what you get? Then you will anyway have this omega n squared left with you, right? So, that is the general method to complete the squares, right? So, do sum of squares. So, what is this factor? Omega n squared minus zeta squared omega n squared. So, immediately you see that omega d squared is going to be equal to omega n squared times 1 minus zeta squared, right? So, immediately you see that this is omega d squared. So, this sum of squares is going to be s plus zeta omega n whole squared plus omega d squared. Do you agree? You expand it, you will see that you will get that one. Okay. So, I think we discussed all these points, right? How to do sum of squares. I am just doing it. So, previously it was with numbers, now it is just with some symbols. That is all the differences. Okay. So, what we have here would be in the denominator s plus zeta omega n plus omega d square and s plus zeta omega n, whole square plus omega d square. Okay, now we are all set, right? So, if you take the inverse Laplace transform, what will you get? We will get 1 minus, what is the inverse Laplace transform of s plus zeta omega n divided by s plus zeta omega n whole square plus omega d square? You remember that multiplication by exponential function, right? See, if Laplace t was f of s, Laplace of e power minus at f of t was f of s plus a, right? So, you see that this is going to be, the inverse Laplace transform is going to be e power minus zeta omega n t cos omega d t, right? So, let me do one more intermediate step. So, this I can rewrite it as 1 by s minus s divided by zeta omega n divided by s plus zeta omega n whole square plus omega d square, okay, minus, let me do this, zeta omega n divided by omega d times omega d divided by s plus zeta omega n whole square plus omega d square, right? I can do this also. What did I do? I just divided and multiplied by omega d in the second term. Why did I do this? So that this term is sin e power minus zeta omega n t sin omega dt, right? So, that is what we have. And this term I can simplify it as minus zeta divided by square root of 1 minus zeta square, correct? I hope it is clear how zeta omega n divided by omega d got simplified like this, right? Because omega d is omega n times square root of 1 minus zeta squared, omega n cancels off, right? So, I get zeta divided by square root of 1 minus zeta squared, and this is going to be e power minus zeta omega n t sin omega d see, this one is going to be just zeta omega n divided by omega n times square root of 1 minus zeta, square root of 1 minus zeta square. So, omega n cancels off, that is why I am left with zeta by square root of 1 minus zeta square, right? And this is that expression, right? Please remember, we wrote this, right? Laplace of e power minus at cos bt, right, was s plus a divided by s plus a whole square plus b square, right? That is what we used here. Similarly, Laplace of e power minus at sine bt is going to be equal to b divided by s plus a whole squared plus b squared. Those are the two properties that we used. Okay. So, immediately we can see that the expression which we derived is the unit step response of the underdamped second order system, right? And we can immediately see that it has two exponential terms. The exponential terms have the real part as the exponent. You can immediately observe that. Of course, in general, the poles, you can write cos omega dt and sin omega dt using the Euler's relationship, and then you will see that the poles will be the exponent. Okay, that also something you can do. Okay, so that is observation number one. So it is stable because the real part is negative. So you can see that as t tends to infinity, the value of y of t tends to 1. Okay, that's why we had this omega n squared u. All right, so see, people may wonder, why are we having omega n squared u on the right hand side rather than u of t? It is just to scale the final value to 1. Okay, nothing more than that. Okay, so you can just have u of t also. Then what will happen is the final value will go to 1 by omega n squared. That's the only thing. Okay, but anyway, that's not a problem for us, right? So we just wrote omega n squared u of t as a convention to make the final value as 1. Okay, and you can see that the response is going to be oscillatory. Why? Because of the presence of cos and sine. And what is the frequency of these cos and sine terms? Omega d. Okay, so now I hope it's clear why it's called damped natural frequency, right? So it is the frequency with which the damped second order system is output is going to respond, right, in the presence of an input, right? So that's what is going to happen. Okay, so that's why it's called as the damped natural frequency. Is it clear? Okay. Now, typically the performance specification. Oh, sorry. Okay, the performance specifications of second order systems are motivated from the above expression. Okay, so that's what typically happens. Okay, like motivated slash derived. Okay, I should say. Okay, so derived from the above expression. Okay, so let's see what these parameters are and how they are calculated and so on. Okay, so that's something which we are going to see now. Is this clear? I hope things are clear until this point. Any questions? Great. Okay. So so we see that, you know, like this is the expression. Okay. So let me draw the how this response would look like. Then we will discuss this. Okay. So typically, if we plot this unit step response. Okay, t 0 y of t, okay, and let's say the value settles down at 1, right? What's going to happen is the following. Okay, so this response of underdamped second order systems, I am drawing an exaggerated diagram just to show a few important concepts. Okay, it's going to essentially oscillate. First overshoot the steady state value, final value of 1. It is going to oscillate around 1 and then finally settle down. So you can see that the cos and the sine functions are multiplied by a decaying exponential. So you see that the envelope of the oscillations is going to decay. Alright, that's why you have a stable system but oscillate. That's okay, right? So what are these performance specifications? Okay, so the first performance specification is what is called as a rise time. TR. Okay, so what is the rise time? It is a time taken. Of course, it really depends on how it's defined. Okay, as far as we are concerned, we will define it in this way. It's time taken for the system to reach 100% of its final value for the first time. Okay, so we'll also shortly see that if you have critically damped and over damped system, like we are going to reach 100% of the value of the output, the final value, right? Time taken for the system output, of course, right, or the response, right? Please note that what is the premise behind these parameters? We are looking at the unit step response of a stable underdamped second order system. Okay, that's how these parameters are defined. Same way what I told you in the morning, that we are looking at the unit step response of a stable first order system to define time constant and settling time there. Similarly, for these parameters that we are going to define now, we are looking at the unit step response of a stable second order underdamped second order system. Okay, please remember that. Okay, so that is understood, right? Because I am deriving it in flow with the derivation, right? So, but I just wanted to explicitly point it out to you, right? Okay. So this is a time taken for the system output response to reach 100% of its value for the first time, right? So, but then you will see that if you have a critically damped or over damped system, the output reaches the final value or 100% of its final value only as t tends to infinity. It will never overshoot like this. Then the rise time definition will change. People will say, okay, what is the time taken for the output to become 90% of the final value? Some people will say 75%. Some people will say 10 to 90%. Okay, someone will say 10 to 75%. Okay, so there are various conventions. But as far as we are concerned, we are going to look at 0% to 100%. Okay, as far as underdamped second order systems are concerned. Okay, that's what we are going to look at. So at what point will it reach the final value of the first time in this diagram? It is here, right? So the rise time TR is this point. Is it clear how we got the rise time TR? Okay, let's read the definition once again. It is the time taken for the system output or the response to reach 100% of its final value for the first time. Okay, that's important, right? For the underdamped second order, that's when it reaches 100% of its final value. Okay, so how do we get an expression for the rise time? Equated to 1, that's it, right? So use this equation. So y at t equals tr is equal to 1, which is nothing but 1 minus e power minus zeta omega n tr multiplying cos omega d tr plus zeta times square root of 1 minus zeta square sin omega d dr. Right, I am just taking the exponential term common from the second and third terms. That's what I have done. Okay, so this implies, what does this imply? This implies that e power minus zeta omega n tr multiplied by cos omega d dr plus zeta divided by square root of 1 minus zeta square sin omega d dr, okay, equals 0, right? This immediately implies that cos omega d dr plus zeta divided by square root of 1 minus zeta square sin omega d dr is equal to 0. Why? Why not? Because, very good. So the rise time is finite, right? So the exponential term, as you said, it's e power term cannot, exponential term cannot be 0. The reason is because tr is finite, right? E power minus zeta omega n t will go to 0 as t tends to infinity. But here we are calculating for a finite rise time, right? Tr. So given a finite value of time, e power minus zeta omega n tr cannot be 0. So this is like product of a and b is equal to 0. If a times b is 0, we can have a to be 0, b to be 0, or both to be 0, right? In this case, e power minus zeta omega tr is certainly not 0. So what should be 0? The term in the square bracket. So if the term in the square bracket is 0, then what will happen? We have tan omega d tr is going to be equal to what? Minus square root of 1 minus zeta squared by zeta. Am I correct? I just took terms to the other side and then cross multiplied. Sin by cos is tan, right? So am I correct in this? So this implies that tr is going to be equal to 1 divided by omega d tan inverse of minus square root of 1 minus zeta squared by zeta. Okay, this people will write it as pi minus beta divided by omega d. Okay, so I hope the first part is clear. How we got 1 by omega d tan inverse of square root of 1 minus zeta squared by zeta. I will explain how we got the second part. Okay, please write it down because I need to scroll up, all right, to explain the second part, how we got it. So this is the expression for the rise time of the underdamped second order system. How do you think we got pi minus beta? What was cos beta? It was zeta. What is tan beta? Please look at the graph. So beta was this angle, right? Tan beta is opposite by adjacent. Opposite was omega d, adjacent was zeta omega n. So what is tan beta? So tan beta was omega d divided by zeta omega n. So this is nothing but square root of 1 minus zeta squared divided by zeta. Correct? But then I have a minus. So that's why we got pi minus beta. Is it clear? See, here I have tan inverse of minus of square root of 1 minus zeta squared by zeta. Right? If I just had tan inverse of square root of 1 minus zeta squared by zeta, I would have had beta. But I have tan inverse of minus square root of 1 minus zeta squared divided by beta. I just used it as pi minus beta. Okay, so that's why, because we need tr to be a positive number, right? That's why we use the periodic nature of the tan function and then wrote it as pi minus beta. Okay, so what it means, even if you graphically plot the poles of the underdamped second order system and you compute beta, you can plug beta, but of course the only catch is that beta should be in radians. Okay, don't plug in beta in degrees into this formula. Okay, beta should be in radians. Okay, because and then you calculate it. Okay, pi is in radians, beta should be in radians, and omega d should be in radians per second. Okay, please remember that. Okay, so see, many people will substitute for the natural frequency and damped natural frequency in hertz. Suppose if someone gives you the natural frequency in hertz, how do you get omega n? It is 2 pi times that fn in hertz. Alright, so please remember that. Okay, those things are extremely important. Okay, so this is the expression for tr. Immediately we can observe that as zeta increases, what happens to rise time? See, as zeta increases, what do you think happens to beta? Zeta is cos beta, right? As zeta increases, what do you think happens to beta? It decreases. Then what do you think happens to rise time? Increases, right? So of course omega d is there, but then you will see that net effect will be an increase in tr. Okay, so what it means is that as we make the system more damped, okay, I would say more damped, as the damping of the system is increased, the rise time increases, or in other words, the system becomes slower to respond. See, what do you mean by rise time decreasing? This graph gets pushed to the right. Okay, so the system's speed of system's response will start to go down, right, as the damping ratio increases. Okay, so that is the implication, okay, of increasing damping ratio on rise time. So conversely, as we make the system damping lower, the system becomes faster, right? That is, the rise time starts to decrease. Okay, so that's one observation we can make. Okay.